This week we had to learn about MOSFET and some of the gate controls. Nowadays, MOSFETs are used for switching transistor. If the gate voltage is bigger than the threshold voltage, the transistor would be on and it operates and becomes a short circuit and let the current flow through them. If the gate voltage is smaller than the threshold voltage, the transistor would be off and become an open circuit, so no current could flow through them. And this is ideal case of transistor, and this is for real transistor. And we have to make this function step-like function. And there are three things we can scaling down the MOSFET: frequency, voltage, potential, and capacitance. What we have to focus in this section is scaling down the capacitance. Scaling down was successful until 113 nanometer node. Below 113 node, simple scaling becomes problematic. As channel becomes smaller, gate controllability becomes weaker, and off current would be different, and on current is different from our targeting model, since velocity saturation that I have talked before. If velocity saturation is occur, current degradation would be occur. Here, what we want is this function, but for real, the ID would be decreased due to the velocity saturation, and the off current will be differ, as you can see in this picture, and it is really big problem of nowadays engineering. And to overcome this problem, we have to control gate. First method is body doping. As you can see in this picture, if we dope in the substrate, the depletion region will be decreased, but nowadays this method is not used widely because there are several problems of random dopant fluctuation and band-to-band tunneling. And next method is by using SOI method, and SOI is an abbreviation of silicon on insulator. We cover silicon oxide on the body here, yellow part. This prevents gate punch channel when it is the punch through. Furthermore, it can prevent leakage current, so each gate controllability would be improved. But this also has some problems. First is it is very expensive, and second is its thermal conductivity is not good. So by in the result of this phenomenon, self-heating problem could occur, such as SSDY and SSGY. And the other problem is that the resistance would be increased as each area is decreasing. Other method of gate control is method of bulk. Use band offset to make quantum well and gather the electrons, as you can see in this band diagram. If we give strain to device, mobility boosting is available, but it is also has several problems such as defect by stress. To eliminate defect, we have to use single crystalline, and it would cost a lot to realization. And since 2010, we start using multi-gate structures such as FinFET, as you can see in this PPT. It is controlled from three sides by gate, as you can see in this diagram, like this, and this is channel. It cut off source drain leakage paths, but some other issues are still exist. Defect and series resistance is the two of some problems. We have to eliminate SY substrate for each economical benefit. And there is another method of gate control, which is gate or around it form of nanowire transistor. Here we are, each gate is different from other structure. And it is excellent in gate control, but main problem is that it is really hard to realize. Especially, it is hard to stack below under the below part here. It also hard to drive current compared to FinFET, and we have developed this technique for academic purpose, but it is not yet to realized in the factory for mass production. It is not prepared. After that, we have learned about more about better way to control gate. There are 4 types of MOSFET here. Bulk MOSFET for A and fully depleted SY for B. Fully depleted SY MOSFET with thin buried oxide and ground plane for C, and double gate MOSFET for D. But I would like to briefly review about C and D. For C, as you see in this diagram, there are box here and ground plane. Box should not be too thin, because if it is too thin, fringing electric field could occur, and row of ground plane is shielding fringing electric field. Each structure is effective, but random dopant fluctuation could occur. Ground plane also could be used as backgate, which is heavily doped, which is similar to D here. For this structure, if we give bias on the top gate and the bottom gate here, gate control would be better than one top gate. By this process, gate leakage would decrease. In the result of this, sub-threshold swing would be improved, and it is really easy to control threshold voltage. But for type D, it is not used widely because it is really hard to realize the two gate, which is top gate and bottom gate. After that, we have learned about FinFET, and this is top view of the FinFET. And there are four important parameters when we design. First is pitch size of fin, and second is gate length, and third is width of fin. And we have to know how to calculate the total width of one fin. And next, we have learned about this structure, and what we have to focus in this section is the neutral length, which is lambda. But it is for real case, the lambda is we have to multiply 6 to lambda to eliminate the problem of leakage current. And yes, and we have to realize we have to memorize this equation for lambda, and this is for one gate, and this is a single gate, and this is double gate, and this is quadruple gate. We have to understand, and we have to know how to use these parameters. Yes, and it was our final lecture, and thank you for hearing.